So our next speaker is Romeu from Madrid, who will be talking about Harris-relevant disordered charged horizon.
Hi, yeah, I will talk about some work I've been doing with Daniel Arean and Sebastian Greninger. And let me for a moment put a pin on the Harris-relevant part and just talk about what I mean by disordered charged horizons and why you should care about them. You should care about them because they should be dual to disordered systems. So that systems with disorder and why you should care about those. For plenty reasons, one of them is that disordered systems, as we've been hearing during the week, they display very cool condensed matter phenomenology. Some of those examples are, for example, and most importantly, these cool phenomenology is present when we have strong interactions. And some of those examples are obviously finite transport, but also Griffith phase transitions. That's when like disorder can basically destroy a phase transition. Anderson localization, disorder fixed points, when disorder holds or sustains your fixed point, or high T superconductivity. And we all know like doping is a very important parameter in the phase space of high TC. And it's an intrinsically disordered effect. So therefore, like you should at least be able to understand. But I think that even more importantly, like life is messy and disorder is always present, even if we don't want it to. So we should at least have some qualitative picture of how it's going to affect or observables like conductivities, entropy, two-point functions, or whatever. And also, we should know if our fixed points are stable under a disorder. Like you could have the coolest superconductor ever, but if it's unstable, once you add a little bit of disorder, then your chances of actually seeing it experimentally become very slim. So yeah, you want some criterion to address if disorder will change the physics or not. Let me backtrack a little bit first and say what I mean by disorder. In perturbative quantum field theory, basically we describe disorder by starting with a clean theory, which I just call S0, and then we deform it with coupling, which is we deform it with an operator whose coupling is space dependent. You can think of this coupling as a density of impurities or something like that. And the point is that this physics shouldn't really depend on the precise location of those impurities. So then you should do some sort of average over this coupling function gamma. And you can use some tricks to convert this, basically this disorder average, the theory, to convert this theory to a homogeneous theory. And basically the class of functions you average over describe the type of disorder that you have. We will mainly focus on what it's called Gaussian white noise that is described basically by these two averages. So noise averages to zero, and the two-point function is basically a non-trivial Valla delta function, where V basically labels the strength of disorder, and N is the number of directions in which you have disorder. Okay, so you have this theory, which is now consists of some copies of your original theory, and it's deformed by this operator O tilde, whose coupling now is a homogeneous coupling. So basically, this means that you can use your standard RGB flow law to see if this coupling will increase or decrease towards the IR. So if you are in a perturbative setup, so like you don't expect corrections to become very relevant, you can compute the scaling dimension of this operator, and this will give you a criterion on how disorder will behave as you go to the IR. So if the scaling dimension of the original operator is below this bound or above this bound, sorry. Once you go to the IR, basically this order will average out and you will flow back to the original clean theory. So nothing interesting there. But if you are below this bound, then once you go to the IR, this order will increase and hopefully will lead you to like new unexciting places. And but again, most importantly, this criterion hinges on the fact that you can compute the scaling dimension of this operator.
What is n?
Sorry?
N?
The number of directions with this order, sorry.
The same as n.
No, M is just the number of, because like you are using the replica trick. I don't want to like, so you have, what you should do is you have M copies of the same theory, and then this operator couples those theories, and then you take M to 0. So this is the number of directions with this order, so like physical directions in which you have this order, and M is just the number of copies, which is just a parameter that you should take to 0.
So you have it in all space directions, n equals d.
Yeah, exactly. Well, d is the number of space-time, so it's d minus 1.
What's the meaning of taking this m to 0?
Well, we can talk about it later. It's not very relevant. It's just some trick that you use to do the disorder average thing. It's some trick in the path integral.
Sorry, I missed n. N is what? This blue
The number of directions with disorder.
number of directions with disorder.
So like I can have disorder along this direction, but then no disorder along this direction.
So I should think of n as being d typically, or d.
Yeah, in a generic system, n is the number of space-time directions, well, space directions, but there are systems which like you have stripped phases, then, so we will see it plays an important role. So yeah, I want to build Harris relevant disorder, so like disorder that will affect my IR. And I will insist to introduce the disorder via the chemical potential. This basically fixes the dimension of my operator that I will couple, and only leaves me like basically a notch to play with to make to ensure that my disorder is relevant. And this forces me to consider only disorder along one direction. This at first, at least to me, it was surprising. But if you think about it, like if you have only direct disorder along one direction and you are a current, basically the disorder looks like a wall. If you have a disorder in more than one direction, then like disorder looks like hills and valleys, and then you can meander around, and then the effect of disorder is less relevant the more directions you have. Okay, so again, I do holography, so I want to reproduce this setup in a holographic setting, see if this law is also true in strongly coupled systems. And what I want to do basically is, reproduce the same thing. I will start with an ADS space, and we all know that if we add some chemical potential, so some charge to the black hole, then the theory in the IR flows towards an ADS2 fixed point, which has all the characteristics that we all know and love, like it has linearity, entropy, and infinite conductivity. And what we want to do now is
I mean, I would worry that then it's important to consider the scaling dimensions of that ADS2 theory. Like, I would imagine that the previous calculation you did is appropriate if mu not equals 0, and then you've
exactly. Well, at least in the UV, it is the right computation to do, right?
yes.
As we will see, this is precisely what we find. Like the computation that you should do is, well, I don't want to spoil the talk, but yeah, it will be important thing. But if you introduce a relevant deformation, you are not even sure if you will find an ADS2 horizon. So yeah, it will turn out to be the case, but at least to me, it's not trivial. So yeah, we will try to cook up a setting in which disorder is relevant and hopefully will lead us to new and exciting places. Just some words on the holographic setup that we use. We use nothing fancy. Basically, we just have a gauge field, a U1 gauge field with some ADS background, well, some coupled to gravity, and we will introduce disorder via the space dependence boundary conditions of the gauge field. We will mainly focus on ADS3 and ADS4. So these are the asymptotics of the gauge field. And we will introduce the space dependence with this horrible function, which is just basically a sum of cosines over different modes. And you see here is the strength of disorder that we saw before. And these cosines have like random phases that will basically ensure that the function is looks like this basically. Then the disorder average will be like just averaging over different phases of this disorder realization. But well, since we will eventually do numerics, we cannot consider infinite modes. And then this disorder realization will introduce for us two length scales, which will correspond to the like highest wave vector in the disorder sum and the lowest, which we call KUV and KI. Then we are basically forced to like consider temperatures inside this regime such that our horizon truly fills the disorder. Otherwise, it's just some inhomogeneity. And then if with disorder average is not truly what we want. Then naively, one would think that we want to take KUV to infinity and KIR to 0. This turns out not to be the right limit, basically because KUV physically what it is you can think of it as the shortest length scale between two impurities. And then we don't expect our samples to be like disordered down to arbitrarily short length scales. So KUV is in some sense physical, and KIR is like the periodicity of your system, the size of your system. So then the right limit is to just pick a KUV, make it constant, and then take as much modes as you can possibly do it. And so then KIR. Some words on the numerical implementation. Basically, yeah, as I was saying before, you have to choose some KUV, some number of modes, a set of random phases, which you would like to average over those, some temperature and some disorder strength. Then solve Einstein-Maxwell equations with a horizon and a random source for the gauge field. Then this turns out to be a nonlinear two-dimensional PD, which is horrible to solve. We have to do it numerically. We solve it using Newton-Raphson. And there's some issues with gauge redundancies, which can be basically solved using this Dirac trick, which.
So it's being solved in the bulk?
Yeah. So we start with boundary conditions on the boundary, then we solve there.
Sorry, what would be the relative size between KUV and the chemical potential?
Exactly. The important thing is KUV over the chemical potential. That's the thing that we fix.
So you will be changing it, or you fix it?
No, that we change it. So that we keep fixed and then we run the computation. But we can do for different choices of KUV.
Is it larger?
It's smaller. So KUV over mu is small. Because you see, like, basically KUV and KIR are fixed by the number of modes that you can have. The number of modes that you can have is fixed by the grid size. So it's large, but not that large. And if we want to explore low temperatures, we are forced to consider basically small KUV.
Yeah, sorry, I could probably ask later, but like how bad is this PDE? Like, is there? So let's see. Yeah, that's the first question.
Like, what do you
How
mean?
long does it take to solve numerically?
Like we used the supercomputer
Okay,
at the IFT, and like each iteration took on the order of minutes.
Is there any hope for the 2D boundary? Boundary would be 2D theory bulk 3D?
I mean, I don't think so, because like it should be a strongly coupled system, which I don't even know what to write. But again, I'm not the best person in numerics, so like this could be like, and probably will, we are trying, but be made more efficient. But at the moment, this is where we stand. Okay, so the results. Again, we are going to focus on ADS3. So this should be dual to a strongly coupled 1+1 dimensional system with a random chemical potential. And for large temperatures, so inside or disorder regime, what we see is precisely that. So, okay, we turn on the source, the disorder source on the UV, on the boundary, and then we see what happens in the horizon. This is, I'm just plotting here the induced metric on the horizon. So we see that the horizon is truly getting inhomogeneous. Here I'm plotting the Ricci scalar, and you see that it's wiggly. So the blue line is for non-zero disorder strength, and the orange line is for zero disorder strength at the same temperature. So now what we want to do is to lower the temperature, always inside the disorder regime. And again, we cooked up everything such that the disorder blew up. And
What's P?
P is proper distance along the horizon. So like since now the horizon is inhomogeneous, you have to take this into account. Coordinate distance is not. Okay, so we expect everything to blow up, and what we see is precisely the opposite thing. So here I'm plotting the standard deviation of the Ricci scalar, which basically amounts to the size of these wiggles. And we see that as we lower the temperature, the size of these wiggles just dies off with temperature. So different colors are different noise strengths, and the gray vertical lines are the disorder regime. So this is KUV, and this is KIR. And even more dramatically, we can compute the entropy, and basically it's completely blind to the disorder strength and just follows the clean case, which is the gray dash line. So yeah, very dramatic. Nothing as we expected. We can compute the conductivities just as we can restate them, the DC conductivity, sorry. We can restate them as integrals over the horizon of basically this thing, which is just the electric field of the horizon. And we see that it gets more homogeneous, and then the conductivity blows up, as you would expect for a clean ion system. So yeah, not at all what we expected. We went up to ADS4, see what if we find something close to what we expected. And basically the same thing happens. For large temperatures, indeed, or horizon becomes inhomogeneous. Now I'm plotting, since I have now a new direction, this corresponds to a killing vector, and this is telling me how much lengths contract and how lengths distort along the perpendicular direction to disorder. And you see it's very wiggly. And again, I plot here some the norm of the Ricci tensor. So it's wiggly. And now I'm plotting here, the average of this thing and the size of those wiggles as we lower the temperature. And now that we see that basically within the disorder regime, so these are these two gray lines, as we lower the temperature, disorder increases the size of, well, the average of this value, then stabilizes within the disorder regime, and then remains constant.
Sorry, so here you are solving like a 3D Einstein.
2D. So, well, it only depends on two directions. So the direction with disorder and then the radial.
So am I being? I thought the bulk would be now 3D.
Yeah. So the bulk now is 4-dimensional, but
Yeah, 14.
then like timing is constant.
Oh,
Like,
there's
I don't have
no-
any dependence in time, nor in this y direction, so I can basically ignore for the.
Oh, yeah.
And these are basically the sizes of the wiggles on the contraction and dilation of the landscape. So what we see is that at low temperatures, what we find is like an inhomogeneous geometry. So because like the size of those wiggles is non-zero, and the disorder has affected like the average distance of the average size of the house. So again, we can compute the entropy, and this is less exciting than we expected. Basically, what we find is that disorder just shifts the value of the entropy at 0 temperature. So, but it leaves unchanged the scaling with temperature. So basically, disorder only affects this term. So yeah, there are some things that are changing. Yeah.
Just go back to the trees. So which going up in the plot is increasing disorder strength?
Yeah. Yeah. Which makes sense, right? So now I'm plotting so yeah, we wanted to understand what was going on. And what we find is basically that somehow the average geometry is basically following the clean one. So here the dashed gray lines are just the analytical solution at 0 disorder strength. And then the orange and the blue lines are the biggest and the lowest disorder strengths that we have. So you can see that basically follows the clean path as a function of the temperature. Sorry, I missed that temperature. But still, even though that the average geometry looks like the clean one, we still have some inhomogeneity. So like it's truly inhomogeneous. Yeah. So again, we can do the same exercise of computing the conductivity over like a sine integral over the horizon, and the result is basically the same. Now we just have this new extra term that measures how the new direction gets disordered. So the inhomogeneity in this new direction, and it is basically, even though that the electric field is still getting homogeneous, this thing is non-zero, so the conductivity just stabilizes within the disorder regime and gives a finite conductivity again, as we expected, since we have a homogeneous geometry, an inhomogeneous geometry. So yeah, what is it going on? We were very confused, and basically we thought the same as Andy said. We should compute what is going on the ADS2 throat. Again, it's non-trivial. Well, at least it's not obvious to me that the ADS2 throat should survive this relevant perturbation. But once it survives and we add some periodic perturbation with wave number k, basically what we can compute the effective mass of this perturbation inside this throat. And okay, so for positive mass would represent a relevant, irrelevant perturbation, so it will die off inside the throat. For zero mass would represent like a marginal one, and for negative mass it would be irrelevant. So what we found basically is that for all Ks, this perturbation is irrelevant. So then it's consistent to what we see, that inhomogeneities die off in the ADS2 case. And if we repeat the same exercise for ADS4, so again, now we have an ADS2 throat times some R2. What we see is that we have the same family of solutions as before, but now a new family appears that goes to 0 as k to the 4th power. So then, even though that is always irrelevant, so like for any finite k, the mass is positive, so it will be an irrelevant perturbation. If we go to small k, will be asymptotically close to a marginal deformation. So then, in some sense, the inhomogeneity survives, but the effect is like, yeah, look like a marginal deformation. So let me summarize what we did. We obtained disorder horizons with Harris relevant disorder. Asymptotically, in asymptotically ADS3 case, what we find is that the IR just goes back to the clean case, explicitly violating the Harris criterion. And in the ADS4 case, what we find is that the inhomogeneity stabilizes within the disorder regime, and this leads to finite coefficients. And but in the IR, what we find is a continuous family of disorder fixed points labeled by the disorder strength. And the average geometry still retains the characteristics, some of the characteristics of the clean fixed point, like the average geometry, the entropy scaling with temperature, and all. And let me just flash some future work that we wanted to address. So it's unclear what will happen in the ADS5 case, because now we can repeat the same throat calculation that we did before, and now we see that inhomogeneities will become relevant. So we expect also from the ADS2 throat case to lead to different things. We would also like to know what happens if we change the disorder. So if we add more directions, now that we've seen that Harris criterion doesn't apply, it's unclear what will happen. If we have some correlations between the disorder, or we source it in a different manner. In general, we would like to know if there's a simple way to predict how will disorder affect the IR. So something like a Harris criterion for disorder for strongly coupled systems. And even further down the road, we would like to understand if we can just obtain these transport coefficients, so like the finite conductivity that we obtain, basically looking at the average geometry that we have, since we already established that it's just the clean. And this will be related to some massive gravity theory. So that's it. Thank you.
I guess maybe did you try the case mu not equals 0? Because then I think, right, like then you should see that this is relevant. So it seems like the easier.
Yeah, at some point we tried, but we had, so it was at the earlier stage of the project. So we had some issues going down to lower temperatures. But again, probably it was just, so since we always normalized everything with the average value of the chemical potential, and we are taking that to 0, probably the code was crashing a little bit. But that's something that we should try to look at.
I mean, because I would say in that case, right, if you have a relevant operator, there's a temperature scale set by V to some power. And that would be the sort of relevant temperature that you need to be low compared to see what happens. I think that's the sort of interesting regime.
Yeah, I agree.
Yeah, I guess sort of another small comment. So I have a former student, Xiaoyang, who wrote a paper 3 years ago on at least sort of resolving this old story with like Hartnell and Santos, and he showed that basically, actually, the sort of weakly Harris relevant regime is the one that gets you a kind of clean Lifshitz fixed point in the IR. So I think that's at least a potential answer to some of the questions.
Yeah,
that we raised.
I mean, yeah, I agree with that, but the point is that in our case, basically because we look at that paper, we truly shouldn't go to like 0 temperature, because like again we have this thing. So basically, the lowest temperature that we have that we can truly check and claim that is a disordered system, it's fixed by KIR, which in turn is fixed by the number of modes that you have. So if you want to go to lower temperatures, you have to also include more modes.
Yes, but I think as I was saying before, the point is that you can ask whether KIR is small compared to the V to whatever power sets the sort of emergent IR energy scale. And as long as that's true, you could have a small KIR and I think still see the interest, like you could still, I think, see the interesting physics in the mu naught equals 0.
No, sure. I agree that you can see that and you should see it. But okay, but yeah, again, for how long the system looks, how long in temperature the system looks disordered depends on the number of modes, and that basically fixes for you the lowest mode that you can have, and so how close to marginal the deformation looks like.
But in the ADS5 case, maybe it's better.
Yeah, in the ADA for sure.
All right, one more question.
It's a related comment. I would have expected that this Harris criterion for the higher dimensional ADS is valid when KUV is larger than the chemical potential. Whereas the disorder only affects to things that are at wavelengths that are corresponding to degrees of freedom on the throat of the black hole. So to me, it doesn't look so surprising that this the ADS2 thing.
I see.
Doing things, determining the relevance or irrelevance.
I mean, even if we will also solve basically the KUV, like solutions with KUV like large, so over 1. And then what we saw is that since we don't have enough modes to like affect the, so we can basically go to enough them. So if we take KUV to be very high, so basically make it over here, then what we saw is that we don't have enough modes for the disorder to stabilize, really, and then just flow back to something.
But it's a technical.
Yeah, that's true. But again, I don't think large KUV would play such a big role.
Well, I think just at which wavelengths is disorder affecting the physics. So if you want to affect to something which is UV, it has to be larger than the chemical potential.
All right, let's thank the speaker again.